Okay, this is a video for Lorena on transformations. I don't really have a good idea of how much of this she's covered in class and whether she just has a few questions on the 4 problems Mom sent, or she really needs a overview of what these things are all about. So I'm going to kind of give a mix of all that. The 4 problems that I saw dealt with, well, reflections, translations, rotations, and dilations. This is where we move a figure around in a coordinate plane and have it reach a different spot. And then that last problem I also saw dealt with the symmetry of an object. And there's 2 kinds of symmetry, line symmetry and rotational symmetry. And you were asked to draw a figure, a quadrilateral that had rotational symmetry but not line symmetry. Okay, and I don't know if you were introduced to this word, isometry. An isometry is a transformation that preserves size and shape. An image that is generated by an isometry is congruent to the pre-image. And so I've drawn arrows to these first 3. A reflection, a translation, and a rotation are isometries. They move a shape to a different spot in the coordinate plane, but the size and shape of the image that's generated is congruent to the pre-image. For a dilation, that's not the case. The size of the image is either usually smaller or larger than the pre-image, although some textbooks introduce a dilation which has a scale factor of 1, and then in that case the image and pre-image are congruent. But normally for a dilation, we're going to say that the scale factor is either less than 1, in which case we have a reduction. I should have typed. Because the image is smaller than the pre-image, so it's reduced. If the image is larger than the pre-image, we have an enlargement. And you can spell enlargement. I'm not going to spell, well, yes I will. Go ahead. Spell it all out. Okay, and this is congruent. Okay, so in problem number 15, we're to identify the dilation and find its scale factor. And the key for finding the scale factor is always to put the size of one of the pre-image segments I'm sorry, I said that wrong. No, the pre-image segment. Let me pause this video. Okay, I just wanted to type this in instead of trying to write it with my mouse. So for a dilation, if you want to figure out what the scale factor is, you take the size of one of the image segments and divide it by the pre-image, and you've got the scale factor. And it's, in other words, it gives you the number that you have to multiply the pre-image by to get the size of the image. So in number 15, I can see you have the answer here, 16 over 6. But identify the dilation. We might say, and normally a textbook would have this point also here labeled as C prime, because it looks like the expectation is that we're mapping segment PC to segment P prime C prime. Actually, I'm surprised that they don't have other letters on here to say that we're actually dilating these little triangles, or this little triangle is the pre-image, and it's mapping to the big triangle. But they don't have any letters here, so I'm making the assumption that they want you to say something like this. P prime C prime is an enlargement with a scale factor is an enlargement of PC with scale factor. Now, how do you figure the scale factor? Well, you got it right here. 16 is the image that goes on top divided by the size of the pre-image, which is 6. That looks like a 6. So 16 divided by 6, but of course that reduces to 8/3. So that's the scale factor. So this sentence right here kind of identifies dilation. And we could say enlargement slash dilation. So again, the image P prime C prime, this segment right here, which has a length of 16, is an enlargement of segment PC, or pre-image PC, with a scale factor of 8/3. Okay, now I'm going to pause the video and bring up the next problem that your mom sent. Let me pause the video. So I'm going to paste in that image, and the problem says to sketch and name a quadrilateral that has rotational symmetry but not line symmetry. Now let's just talk for a minute about what we mean by line symmetry and rotational symmetry. Let me draw a figure that's not a polygon. For example, you used to probably create these when you're in 2nd grade. Valentine's, shape of a heart. That shape has line symmetry. And the line of symmetry, well, let me use a line drawing tool, is this right here. In other words, a symmetry, particular shape, is like a mirror. You can look in the mirror and you see the same shape on both sides. Or you could think of it this way. If you fold a piece of paper along the line of symmetry, if the two halves lie on top of each other, then the figure has line symmetry. This rotational symmetry means you usually find a point right in the middle of the shape and then start rotating it like it's on a pin and see if you can get it to lie. Let me get this figure right here. You start spinning it and see if you can get the spin to lie on top of the image to lie on top of the original shape. This heart doesn't have rotational symmetry because if I have to rotate 360 degrees to get back to where it was. But if I have a shape that's like a star, and I don't know how good I'm going to be at drawing a star. Assuming all these stars making, or all these triangles making up the star are congruent, this star could have rotational symmetry, and that is if I rotate this way around this point in the middle, I will not be able to distinguish between the original shape and where it ends up now. So that's what we mean by rotational symmetry. You can rotate the figure some number of degrees and it will lie right on top of itself. Okay, so a quadrilateral that has both line symmetry and rotational symmetry is a square, for example. And this square has several lines of symmetry. Let me go to a different color. So this is a line of symmetry, because if I fold along the square along that line, the two halves are going to lie right on top of each other. This is also a line of symmetry, because if I fold along that line, it serves as a mirror, or the right half will lie on top of the left half. And similarly, this is a line of symmetry. And guess, okay. By the same token, the square has rotational symmetry. I want to use it because if I rotate, as if I picture sticking a pin in that red circle and then spinning the square. If I spin it from here to here, I won't be able to tell that the square is different than it was originally. It's going to lie right on top. And I can spin it from there to there, and I could spin this point all the way down to here. Or even all the way to here. So the square has rotational symmetry. So for this problem, sketch and name a quadrilateral that has rotational symmetry but not line symmetry. The typical example used for that is a parallelogram that is not a rhombus. So let's see if I can draw a line here. Parallelogram. I drew. And I didn't draw a very good parallelogram. You get the idea. Okay, it doesn't matter where you draw a line, this shape does not have line symmetry. I can try drawing some of the lines that I did for, like right down. If I fold along that line, this half does not match this half. And by the same token, if this is a line of symmetry and I fold, this point right here, this vertex, is not going to lie on top of this one. It's going to be up in here somewhere. So the parallelogram does not have line symmetry. But if you rotate this point, I'm trying to get a line here, all the way over to here, spinning across this point right here, stick a pin in the middle of the parallelogram and spin it, the image is going to lie on top of the pre-image. So if you label a parallelogram A, B, C, D, I think you're going to have an answer for number 13. Sketch and name a quadrilateral that has rotational symmetry, but not line symmetry. Okay, I'm going to pause the video. I'm going to go to the next page. And let me pause the video. Okay, so problem number 21, multiple choice. A double reflection across intersecting lines results in what type of transformation? Okay, now here's where I don't know exactly how much detail to go into, Lorena. So I'm going to maybe be a little more complex than you need, but not as detailed as I could be. Okay, a translation is the composition of two reflections. A rotation is the composition of two reflections. It is just that the lines about which the pre-image is reflected are different. That's why you get different results. Now, what do for a translation for this triangle, we just mean we're going to move it in this direction, perhaps. I should have had a line with an arrow on it, and translate it over to here. And so we'll get, I'm going to draw another triangle. I might not get it exactly the same shape. But you get the idea. See if I can move it a little bit. Whoop. Yeah. Okay, so I moved this triangle to the right by sliding it. And it's still got the same shape and size. It's congruent, or at least it's supposed to be. Okay, but the truth is that I could get from here to here with a composition of two reflections. Now, what are those reflections? Well, this line right here is called the translation line. But actually, that's a translation line. We're sliding the figure along that line. Okay. And if I take two lines, the distance from here to here is the translation distance. And all of these points, like this point, will slide the same distance as the top vertex, and this bottom point will slide the same distance. Okay, so the translation distance is the same for all the points on the original triangle. They're all sliding the same distance to the right. The reflection, the combination of reflections, works like this. See if I can erase those, okay? If I can find, let me just make up a number for this translation distance. Let's say that this distance here is 50. Well, if I can get two lines that are perpendicular to this translation line, so these are right angles, and that are half this distance apart, like this. So this distance is 25. If I reflect this triangle over the first line, I'll call it L sub 1, I'll kind of flip it. I don't slide it, I flip it over this line. I reflect it over the line. And then if I reflect that image over this line, the second line, L sub 2, I will get this image. So that's why we say a translation is the composition of two reflections, but it's got to be over the right kind of lines. They have to be perpendicular to the translation line, a line that is joining a pre-image point with its image point. Okay. Now, if I rotate a picture, and I'm going to pause the recording. Okay, now I'm going to talk about a rotation. So a point like this is called the center of the rotation. And the fact is that if I stick a pin in here and then picture rotating this triangle like this, I have rotated the triangle about this center of the rotation. And the size is still the same. The angle of rotation is something like this. So I've rotated this triangle this number of degrees around this center of rotation. Okay, and here we've made a comment that a rotation is the composition of two reflections. Okay, but where are the lines that you have to reflect the triangle over in order to end up here? Reflecting instead of rotating. Well, it turns out that if this is, let's say 120 degrees, 120 degree rotation, you need to have an angle in here created by two rays going through the center of rotation that form a 60-degree angle, half of the original rotation. If you reflect this triangle over this line and then reflect that image over the second line, you'll end up here. Okay, I'm not going to try to prove that to you. I'm not going to do any calculations. Just accept the fact that a translation is the composition of two reflections, but the lines about which you reflect are perpendicular to the line of translation. A rotation is the composition of two reflections, but the lines intersect at the center of the rotation, and the angle between these two lines is half of the original. And here, this distance between the two parallel lines is half of the translation distance, as I showed in that first screen. So anyway, how do we answer this question? A double reflection across intersecting lines, well, that's what this means, intersecting lines. These rays intersect, so this must be a rotation. If it's set across parallel lines, it would be a translation. Okay. Now, for number 22, determine whether the figure has rotation. I got no picture to look at, so I can't help you with that one. If so, describe the angles of rotation and map the figure onto itself. I would just be guessing what the figure looks like, so I'm not going to try to do that. I'm going to pause the video and bring up the last. Okay, here we go with this last problem. I think it looks like number 25 maybe. But what we have is a reflection across one of two parallel lines. This line right here, make it a line, is the translation line. Okay, we're sliding the original triangle this far. And by the way, I could do the same. For A prime, and A double prime. Okay, I can pick one of those lines of translation and indicate that K line K and line M are not only parallel to each other, but they should be perpendicular to one of the lines of translation. Doesn't look like it in this diagram. But the key is that this distance right here, let me go to red, the distance between the parallel lines has to be half the translation distance. So this from C to C double prime is the translation distance. I could put these two parallel lines anywhere. I could slide them further to the right. It doesn't matter. They just have to be perpendicular to a line of translation, and they have to be half the distance apart that the image and pre-image are. So what do they tell us here? The distance between K and M is 1.7. So this distance right here is 1.7. That has to be half the distance between C and C double prime. So all we have to do is multiply 2 times 1.7, and that equals 3.4. Okay. That's how far apart C and C prime are. And that's basically all there is to it. I hope I didn't go into too much detail, that I went into enough detail. I'm sorry we didn't get to meet tonight, but I'm going to send the video. If it proves to be too long to upload on Wyzant, then I'll send you a link and I'll upload it to YouTube. Okay? I'm going to end the video so it's not too long.